This is the second webinar on the fifth day of UNAVCO's short course on GNSS data processing and analysis with Gamut Globe K and Track. My name is Mike Floyd and I'll be presenting this lecture showing some examples of things that you can do using Track. So what we'll look at is various different types of uses and some examples of those uses. So we'll look at a kinematic example, what we call a kinematic static example, and some true static examples. So in the first category, we will look at GNSS seismology, which is basically using GNSS sites to measure displacement at a high rate during a seismic event, essentially turning the GNSS equipment into a seismometer. In the kinematic static example, we'll look at some rapid deformation where a site is static, moves, becomes static again, and moves again. And then also another example of episodic and continuous deformation. For the static examples, we will look at short static occupations. So this would be where you have a very short record of data, perhaps just 20 or 30 minutes, which is generally not good enough to produce a solution in Gamut. But the site nonetheless is actually a static site. It just has very short span of measurements. We can actually use Track, even though it's a kinematic module, to calculate a static position in that case. And we will also look at deciphering interference in an antenna. So for example, if you have an antenna that has been moved and you didn't know exactly when it was moved, then we could look at epoch by epoch track processing to identify the time of disturbance. So it's important to remember the rule of thumb for proportional errors here, that the error on the baseline is going to be approximately equal to the error in the satellites multiplied by the baseline length between sites divided by the height of the satellites. So we bring this up really just in the sense that Track is a true baseline processing program. We have a reference site, a fixed site, and a site that we are interested in determining its motion or perhaps static position that will be some distance away from the reference site. And the closer the kinematic site is to the reference site, the better our results will be. And if it's very close, we can actually use L1 and L2 data independently. Otherwise, Track still uses that ionosphere-free or first-order ionosphere-free LC linear combination. So example one here is this example of GNSS seismology, and we will look at the 2010 El Mayor Cucapá earthquake in Baja California, just over the southern border of the US into northern Mexico. We'll look at 5 Hertz results. So this is 5 records per second, and later look at some longer baseline processing for the sites as well. So the Track results here are generated in 2 steps. The first step uses 0 process noise. So essentially it fixes the position of the sites except during the time of the earthquake. So we keep the sites static, fixed, unless we are at the time of the earthquake, in which case the sites are allowed to move. Now this helps with fixing the ambiguities or helping to estimate the ambiguities in a preliminary run. And once we have done that, the second run, the final results, will be generated by feeding back into Track the estimates of the ambiguities from the first solution using this -a option. Or there's also an option in the Track command file that can allow you to read in an ambiguity estimate list. Once we have some of the ambiguities fixed, we can allow process noise so that the sites actually show us what level of noise they have in the phase and pseudo range, and also allow the sites to move freely during the earthquake. But with the ambiguities fixed, it strengthens our solution over time. And in order to help with that process, we run a first solution where we keep the sites as static as possible. So as I said previously, with a long baseline, the ambiguity resolution and the estimates are done with the linear combination. With very short baselines, about 1 kilometer or 2, perhaps at most, we can actually use the L1 and L2 phase observables independently to increase the signal to noise ratio. But on longer baselines, we would just stick with the LC observable. So let's introduce you to the earthquake itself. This is the California-Mexico border here. This is the Salton Sea, for those of you who are familiar with the area. And the earthquake occurred here about 50 kilometers or so inside Mexico in Laguna Salada, or just to the east of Laguna Salada. And we can see here the deformation of sites in Southern California due to the displacement during the earthquake. We see here some examples. For example, P494 had about 20 centimeters, 200 millimeters of displacement. P496 had about the same, 18 centimeters of displacement. P497, which is just hidden here, but there's the vector, had about 97 millimeters of displacement, 10 centimeters of displacement, and so on as we go further and further away from the earthquake. And we'll look at some of these sites in the next slides to see how they moved, not only the static displacement during the earthquake, but actually the dynamic displacement as the seismic waves passed the sites. So we're going to, here's the earthquake epicenter down here. We're now zooming out across all of California and much of the southwestern United States. We are going to use this site here in the Central Valley of California to be our fixed reference site for the 5 Hertz positioning. And later on, we're actually going to see how this site moves relative to this site here using 1 Hertz data. Just to, because we will fix this site to process this data, we also really want to know exactly how this site moved, if at all. So we need to form a second baseline over here, which will help us determine if our fixed site actually moved as well. If our fixed site moves, if our reference site moves and we fixed its position, that position will actually be propagated to the network down here. So this shows you the P496 site, which showed about the 20 centimeters of displacement. And this shows you the north time series at 5 Hertz rate. Here you can see that this is seconds after the event, the earthquake rupture, for about 600 seconds, about 10 minutes or so after the event. In the orange is the east component, in the gray is the north component, and you can see very clearly the arrival of large surface waves from the earthquake around about 35 to 40 seconds after the initiation of the rupture. There's another thing in this plot that you will notice. Not only is there the wave train coming through, but actually you can see the static displacement as the site settles down at its new static position. And in this case, most of the displacement is in the north component. We start at about 0 here, and we end at something like 200 millimeters there, you can see. This scale here is for the east component, which again starts at about 0 and ends at about 0. So this static displacement on the east component is very small. Most of the displacement on this site was in the north component. Similarly with P494, which had about 18 centimeters of displacement, we see very similar thing, slightly reduced amplitude here. The site's a little bit further away. We see slightly smaller motion in the static there, but very similar idea. And we can continue to go through some of those sites, and you see very similar surface wave patterns coming through before the site settles down again. And you can see at a time that is 5 to 10 minutes after the earthquake, that this is the sort of level of noise that we are seeing from the phase measurements themselves. So this is what we would normally fix here and here. In the first run, we would fix this all to 0 to help with ambiguity resolution. Once we have the ambiguities fixed, we can free up the solution as well by applying process noise to allow the data noise, the phase noise, to really show itself in the resulting time series. As we go further away, the amplitude again of those surface waves and the period of the surface waves changes. We're now really reduced to longer period surface waves with lower magnitude. But we start to see another signal popping into the time series. And as I go through some of these sites, you will see that signal again and again crop up. This is happening around about 220 seconds, 3.5 minutes after the earthquake. And so many people might say, well, what is this? Is this a secondary rupture? Is this some kind of instability in the earthquake? Is it perhaps an aftershock, something like that? Well, actually, as I noted previously, we need to take into account the motion of the fixed site as well, because implicitly we are fixing our reference site and processing all other sites relative to that site. And this little blip here is actually the motion of the reference site, which we have considered fixed, but it's moving at about 3.5 minutes after the earthquake as the surface waves eventually reach the distant fixed site. Because the site is fixed, any relative motion between the reference site and our site that we are processing is manifest as a motion in the kinematic site itself. So at this point, the kinematic site is not actually moving. What's really happening is the fixed site is moving, but because of the change in baseline length, it seems to be a motion of P742. And we can see that in this next graph, which shows the motion of our fixed site, P795, versus the P033 site, I think it was in Central Valley of California. For comparison, we show a zoom of that motion at the sites that we just saw about 220 seconds after the event. And in red, we see the motion of P725, our reference site, at 1 Hertz rate compared to the site in the Central Valley of California. Here, this time series has been multiplied by -1 because the motion of the reference site, if it's fixed, will actually manifest itself as a mirror image in the kinematic sites. So that shows you that actually this motion here in all of these sites matches exactly the motion of the site that we fixed. So these secondary features are actually a motion of the reference site. Our second example is an example of rapid deformation. So the context here is that in South America, we had a major subduction zone earthquake, followed by 2 aftershocks, which were normal faulting earthquakes, about 15 minutes apart. And the author of this paper was using INSAR to try to determine the motion that occurred, or the displacement that occurred in these earthquakes. But the INSAR data was collected before both earthquakes and then only after both earthquakes had occurred, because the earthquakes were so close together. So in this case, the INSAR shows a cumulative deformation between these two aftershocks, and there's no way to separate the events. One way that we could separate the events is actually to process epoch by epoch GNSS processing rather than batch. So batch processing would be to take all of the data in one go and produce one time series point for an entire day, for example. That's what Gamut does. Track, we are going to use each 30-second by 30-second record, or 1 Hertz record, or 5 Hertz record. We're going to produce a position for every single one of those observations rather than averaging the observations in batch. So the first thing to point out is that we need to select what we consider our fixed site to be, our reference site. And these are the sites that were available for this study. There were several along the coast and then one fairly close inland, although the distance here is still around about 100 kilometers from the coast. But we select this site CURY to be our reference site for the following reasons. Number one, there was this main subduction earthquake highlighted sort of here in white shading. And we would like to be as far away from any post-seismic deformation as possible. It was a very large event, so it is possible that post-seismic deformation would also be occurring inland. But the further away we can get, the better, so that we are not corrupted by any after effects of the main subduction earthquake. Secondly, it's outside of the deformation zone of the two aftershocks that we are wishing to study, the two aftershocks that occurred 15 minutes apart. And you can see here in the INSAR these sort of circular fringes that are indicative of the deformation pattern associated with the cumulative displacement. Remember, the INSAR cannot distinguish between the two earthquakes separately. This is the cumulative displacement we're seeing of the two earthquakes. And furthermore, luckily, CURY actually lies on the nodal plane of those aftershock fault planes. So the aftershocks occurred on fault planes that were approximately in this direction, which means most of the deformation will be seen in this direction, since they were normal faulting earthquakes. And so the advantage of being on the nodal plane or along strike is that there's very little deformation in that nodal plane area. So again, we run a preliminary run to help constrain the ambiguities for for the final run. And this just demonstrates what we said previously about the El Mayor-Cucapá earthquake, but also this event as well, that we have the sites that we wish to process. They are loose in position, but the process noise, the amount of the amount that they are allowed to move with time, is set to 0. So these sites are considered static by setting the process noise, these zeros at the end of the line, to 0. However, we do know that these sites will move during the earthquakes themselves. So we include this time-dependent process noise command, which allows process noise between these two periods. So for these two periods, the first 3 lines here is the epoch of the first aftershock. So we allow it to move for 1 recorded epoch. And then the second set of 3 lines here is the time at which the second earthquake occurred. So we allow the sites to move at the epoch of the second earthquake. It is worth noting here that these times are given relative to the times that are in the RINEX file. The RINEX file times are given in GPS time, which is slightly different to UTC. Most seismic studies, most seismology studies, most seismology reports will use UTC for epicenter time, hypercenter time, centroid time. And so we need to know what the difference between GPS time and UTC is in order to get these times correct. Currently, as of the recording of this, webinar, the difference between UTC and GPS time is 18 seconds. At the time of this earthquake, I can't remember what it was, but it was perhaps 15 or 16 seconds. So we need to take that into account when we compare times in the RINEX files and the track command files to the times that are reported for the earthquake. Nevertheless, this is the resulting time series that we see. It looks rather odd because the time series is static at the time before the first earthquake. Then the site is allowed to move for one epoch because of these time-dependent process lines here, and then it is fixed to be static again. And at the time of the second earthquake, for one epoch, it is allowed to move and again remains static thereafter. This is the plot of the atmospheric contribution, the atmospheric delay. Over such a short time, this could be restricted with some constraints on the process noise. This is about 2.5 hours here, and the atmospheric delay is changing by several centimeters, which is probably a little bit high for only 2.5 hours. So we could constrain this atmospheric parameter as well in order to help with the ambiguity resolution too. But during this time, the reason we do this sort of static, move, static, move, static type run is to help with the ambiguity resolution between the times of motion. So the next thing that we do, there's the times of the earthquake. The next thing we do is we firstly update our a priori coordinates. The a priori coordinate is the first coordinate. A priori means beforehand, before, as opposed to a posteriori. But so the coordinate that you're really looking for is this very first coordinate. But since we processed our data, you can see that there is a slight difference between the 0 line here and our first coordinate. So we can update the coordinate accordingly to be here rather than at the 0 line from the first run. And now we can update our constraints on the coordinates. Here was very loose. Now we know our coordinates much better. So again, we can assist ambiguity resolution by actually tightening the constraints on the initial position. That the updated a priori coordinates can be run with the sitepos command. And we've run the same thing again, just to improve our solution again, fixed, except for the time of the earthquake. And just to reiterate what I said before, this axis is actually marked in UTC, but that is not correct. The axis label is wrong. This is GPS time, not UTC, so we need to add the appropriate number of leap seconds if we are to compare between the GNSS and the seismology. So in the final run, what we do is we read out the final ambiguity, the resolved ambiguity estimates into a file, any file name. You could call it track.amb. And now we are going to allow the sites to move at all times. So we completely loosen the sites, they are free to move, and we include the ambiguity file in the command file, or we can use that -a option in the track command line itself. And this is the resulting time series. So now you can see the noise in the phase data itself. We are not fixing anything anymore. We are allowing the phase noise, the pseudo-range noise, to be seen in the time series. There's a little bit of an odd patch here, which may be due to reduced satellite visibility. Perhaps the ambiguities being fixed in this region weren't as good as in the other areas that you see here with the smaller error bars. But hopefully you can still see the same pattern as we saw before. In the east component, the site starts here. It moves to the west after the first earthquake. and then moves back to the east after the second earthquake. Similarly, in the up component, very clearly, the site moves down in the first earthquake and then back up in the second earthquake. The north component doesn't actually show too much, perhaps some southward motion in the first earthquake, but very little that can be seen in the second earthquake. So the main point to take home here is that we go west, then east, and then down, and then up. So the initial hypothesis for this work, when looking at the INSAR, was that these two upper crustal normal faulting aftershocks took place on antithetic normal faults in the upper plate. So that would look something like this. This is west, east is to the right. Here is the subduction zone, the coast of South America, and our site LEMU that you just saw the time series for. The initial hypothesis was that we had antithetic faults like this around the site. And so during the first aftershock, where LEMU was on the hanging wall of the fault plane, it moves down and to the west. And then in the second earthquake, again, we're on the hanging wall. And so again, LEMU would be predicted to move down and east. But this is not what we saw in the time series. We saw a westward motion and then an eastward motion, so the horizontal is correct here. But in the vertical, we saw a downward motion and then an upward motion during the second aftershock, which does not fit with this model. So the hypothesis was changed, and the final conclusion is that the site LEMU is on the hanging wall of the first earthquake in exactly the same situation as we see here, but it's on the foot wall of the second aftershock. And therefore the faults must be synthetic and not antithetic, like this. Here we have the same initial shock. There's the first aftershock. And then the motion during the second aftershock is LEMU actually sits on the extension of the fault plane on the hanging wall side. So we move east again, but actually we move back up. So this is an example of where track could actually help differentiate between two earthquakes that happen very close together, just 15 minutes apart, that you may not see from daily processing of the GNSS or INSAR, where the temporal resolution is just not enough to differentiate between these two earthquakes. Now, it must be said that there was a little bit of a problem with this data. I'm still not quite sure of the reason why, but I had to use this tool cview to try and get an idea of what the data looked like. And this shows you what normal data might look like. This is phase data here, L1 on top, L2 in the middle, and LC in the third panel here. These are your standard parabola looking measurements for the phase. This is the satellite rising, passing overhead, and then going back down the sky. So you see two passes of the satellite here within about 24 hours of one another. The satellite rises, falls and sets, goes out of view below the Earth, and then rises, goes overhead and sets again. This is a perfectly normal pattern of phase measurements at any site. Sometimes you'll see satellites with problems. You can see here some cycle slips, which would normally be fixed in AutoClean or in track. So for AutoClean, we would try and create a nice parabola, hyperbola again, by fixing these steps in the phase, and track has a similar algorithm to do the same thing. The problem that I came up against while doing this processing was actually to do with some of these cycle slips that happened very close to the time of the earthquake. So we're going to zoom in on this region here. You can see largely what these cycle slips did. And if we zoom in here, you can see those cycle slips in a bit more detail. So it happened in L1 and L2. The cycle slip went one way and then seemed to go to the other. And some might say, well, okay, isn't this just evidence of the motion during the earthquake? Was there, a difference in phase because of the motion of the earthquake? And that may well be true, but actually the time of the earthquakes were here, this line and this line here. So these cycle slips were not happening at the time of the earthquake, but nevertheless, track had some problems identifying and fixing these cycle slips. And so what I actually had to do was I had to go in, look at the data in cview and manually add a definition of the cycle slip here. So for this site, ILOC, for satellite number 17, at this time and this time here, I identify a user additional bias flag, user add bias flag for this site and this satellite at this time. And that helps track just to identify where it needs to do some fixing in the data. So it's always fun to play with cview to actually see the phase data that you're using. And sometimes it's actually very helpful for dealing with problems in the processing so that you can potentially add manual flags. So in our third example, we are going to look at episodic and continuous deformation. So here, what we are going to do is we are going to look at the motion of a glacier in Antarctica. And we're going to look at that motion on a sub-daily basis. But in order to do that, first we need to actually identify a fixed site in order to use as a reference site. So what I'm going to do is I will first do a normal gamut globe K processing of the networks that are available around the glacier. And then from that, we'll find a candidate stable site. And we also ensure that we have accurate coordinates for that reference site. Then in the track processing, we will use one or more, perhaps a network of nearby bedrock sites as the reference sites for the kinematic processing on the ice flow. One fixed site is the natural, the way of doing track. Only one site can technically be set as fixed. But as you saw in previous examples, we can actually fix the position of other sites by providing a zero process noise constraint on them. So we can actually have multiple fixed sites, although only one can technically be defined as fixed. The other ones we would have to just add zero process noise. And the ambiguities must still be resolved correctly in order to get the best results. So going forward on that, here is a picture of the current UNAVCO DAI, Data Archive Interface. This runs on Flash technology. Flash will be going away, becoming end of life and deprecated at the end of this year, 2020. And UNAVCO is currently rebuilding this interface to move beyond Flash. So this is the current address, but please keep your eyes out for a new interface coming at some point within the next 6 months or so. This address will change by the end of 2020, we hope. So here is a search of Antarctica in the UNAVCO database, and I found all these sites that are available publicly from UNAVCO. So I decided to process all of these in gamut and globe K to try and find what a stable site for my reference site would be. And just for reference, the ice flow that we're going to be looking at is here. So the first question we have to ask ourselves is, are we looking at a site that we want to use as reference on ice flow or bedrock? Ideally, we want our reference site to be fixed with a well-known coordinate. So here's a candidate site. This is the time series for 1 week that I processed. As you can see, nice repeatability here, very consistent results from day to day, RAMG. And so the question is this ice flow or bedrock? And Hopefully most of you will appreciate the fact that this is bedrock. It's not moving very much at all over a week's period. And indeed, here is a picture of the site, nicely stuck on this mountainside, slightly snow-covered on one side, nice rocky bedrock on the other, and there it is attached to bedrock. So that's a candidate that we could use for our reference site for the eventual track processing. Here's another site, BUMS. Again, good repeatability, nice processing, and again, hopefully you will be able to guess correctly that this is a bedrock site. I don't have a picture of this one, but it is here in the Transantarctic Mountains. It looks like a lot of snow, but believe it or not, it is on bedrock outcrop in the mountains here. So this again is a bedrock site. Here's another site, UTHW, and here is the gamut processing from day to day. Now we are seeing motions over a week of several centimeters. In fact, decimeters of motion over the week. Very little in the vertical, but certainly very clear in the north and the east. And so hopefully here you will be able to guess that this site is indeed on an ice flow, not on bedrock. So this is not a very good reference site because this site itself is moving pretty rapidly relative to fixed bedrock around it. So we do not want to use this site for our reference site. Here's another one, FALL, which looks very similar to the first two, and you would be quite right if you guessed that this site is on bedrock. And here is a picture of it. Again, some bedrock outcropping. And here's another site, one last site, AMU2, again shows that motion over a week. This is moving fairly rapidly, not quite as quickly as the one that we saw before. This is really just a few centimeters over a week now. But I wonder if anyone knows where AMU2 is. And if you don't, the AMU might be a clue. This is the Amundsen Scott base at the South Pole. Here is the site on the base building at the South Pole. And I like this example because it really shows, there's the South Pole there, that's the location of AMU2. And I really like this example just because it simply shows that the South Pole is covered in ice, and that ice actually moves. So this is why they often have to move the ceremonial South Pole every year or so. I think they have a moving ceremony because the ice above the South Pole has actually moved. So they need to move the literal pole, the ceremonial pole, back to the actual rotation pole position once a year because of this motion. I believe that they still do that ceremonial South Pole repositioning. So we're going to use FALL, RAMG and BUMS as our fixed sites to process these sites that we actually see on the ice flow. And here is an example of one of them, LA14, which shows basically no motion, static motion, and then over the period of about 30 to 45 minutes, it actually moves, and then it stops again, and then it moves, and then it stops again for a while. And about twice per day, we see these motions of the ice flow for about 30 to 45 minutes in both the horizontal components, the east and the north direction. The vertical component is mostly just noise that you can see here. It doesn't really have the same movement detected in the vertical component. Another site that we see is MG01. And again, you see here these same times of about 30 to 45 minutes of motion. But in between times, the site is not as static as we see in this site here. In the vertical component, we now see a very systematic signal that is indicative of something clearly different to this site here. And I wonder if you can think briefly about what might be the difference between these two sites. The difference is actually that this site here is above the grounding line of the ice flow. So this site is where the ice flow is sitting on top of solid ground. This site here is below the grounding line of the ice flow. So at this site, the ice flow is actually sitting directly on top of the ocean. And as a consequence, you see the result of the ocean tides flexing the ice sheet. So this is a signal of flexure of the ice sheet as it responds to the rising and falling tides beneath it. And you see a very sort of similar, but a little bit less of an amplitude in the horizontal components as well. The asterisk here is just to declare that FALL is the fixed site with the F option in the OBS site, OBS file option in the track command file. And BUMS and RAMG are technically kinematic sites with a K flag, but they're constrained to 0 process noise. And I used 3 here just to give a little bit more of an azimuthal coverage to my network. So here's some justification for the way that we did the track experiment. We wish to apply our own temporal constraints. We have moving sites, so let's be clear on the units that we're working in when we declare the temporally correlated noise. We're going to be working in seconds. The atmosphere is more stable in Antarctica. There's very cold, high pressure usually, and this is evident by looking at the atmospheric delays in the gamut O file, which are very stable. So we can constrain the atmosphere here to not change very much with time. And remember here, this is, I think, meters per second squared is the unit here, and we've declared that the time unit is seconds. So that relates to these numbers here. Previous studies have shown that the displacement rates are about 0.5 meters over about 30 minutes. So from that, we can calculate again a variance that we can apply to the moving sites during the time of motion that is in meters squared per second that would basically add up over time to allow about 0.5 meters over 30 minutes. Next, we have an example of short static occupations. So this is where we might have short spans of data, for example, just 30 minutes. It may be processed in gamut, but sometimes the results are not very good. The data may be thrown out as being too short to adequately produce a result in autoclean, especially if it's not of very high quality. So we could use track here to do a short static approach, where we actually, again, allow 0 process noise on the sites that we wish to process relative to the fixed continuously recording and well-positioned base site. So here's a base site with a long session and an accurate a priori coordinate calculated in gamut. Around the site that maybe is set up for 24 hours or 48 hours, we have another site that is only recording perhaps 30 minutes of data, and we want to know where this site is. So we can use the well-known coordinate of the fixed site and just simply process track using this baseline where here this is fixed and this has 0 process noise, so that we only get one single position for the whole 30 minutes of data. We could do that for several roving sites, and in the end, we would build a network of short static occupations relative to a longer fixed site and build our network this way. It's a little bit more complicated than normal gamut processing to build a network, but nonetheless, you can get results this way. And now I'll show you some of the results that I've done previously. This is a couple of sites from the Geysers geothermal field in California. And what you will see here is that in red, in the orange bars here, these are data that were collected for a long enough time that they were actually processed in gamut. So these data are a number of hours processed in gamut the usual way. The other points that you see on these time series were processed in the short static approach with track. You can see the error bars are larger. There's a bit more motion here, so the error bars are reduced in size. We do have an outlier here, which is perhaps something to do with the processing, maybe ambiguity resolution, or maybe the site was set up over the wrong position. But nevertheless, I hope that you can see that this processing strategy is actually very consistent with the gamut processing that we do for the orange bars. We can exclude this outlier just as we would exclude any outlier, but generally that track short static strategy is very effective at still making these very short occupations quite usable. When you're doing survey work, unfortunately, sometimes this happens and you see that someone may be pushed over the site. In this case, we've talked with the local owner of a nearby house, and he's reported to us that this area is particularly windy, and it is very likely that this site has actually just been blown over, despite our best efforts to lock it down with rocks. In this particular site, this has happened a number of times, and it has usually coincided with very extreme winds. So is there anything that we can do about this? Well, yes, we can use track to try and figure out exactly when the site tipped over, and then reduce our RAMG file to only the part of the data before it fell over. We do not want to process this site in gamut, where half the data is from the antenna looking like this, and half the data is from the antenna looking like this in the lower right corner. I should credit my colleague, Gareth Funning at the University of California, Riverside for these photographs. The height of the antenna when it was set up is 1.281 meters, so bear that in mind, please, as we move on to the next slides. So the first thing is we run track. We're just with loose constraints to identify the probable epoch of disturbance, and then we can update the a priori position, again this first position, and rerun track for the solution. You can see here in the time series that this is the setup time, and at about 7:36 local time, we see that the site shifts. It falls by just over 1 meter, and so that is a verification of the fact that this is the antenna on the tripod and then on the ground for the rest of the time. You can see that it still does record things, but the orientation of the antenna is different here. It might be rolling around a little bit, so this data here is effectively useless, and we only want to use this first 5 or 6 hours of data in any future gamut processing. So we would then rerun tech, or with any way that you could cut the RAMG file at the epoch of disturbance, so you don't pass on bad data to other people. Here's a more complex example. Again, the site here is being set up. This road here has a bus stop, and behind the picture is a school. The school buses drop off the children here. The children gather on this pathway before their teacher meets them and walks them over to the school building. The height here of the antenna is 1.04 meters, and the resulting track run looks like this. So in this case, what we have is a site that runs along nicely, gets disturbed, falls down, and then is repositioned, apparently, back to its original position. Now, when we came back to this site, we measured the site again when we took the antenna down, as one should do, and I noticed that there was a few centimeters of difference of offset between the antenna center and the center of the mark, and also the height was slightly different. This is what made me suspicious that the antenna had actually been moved sometime during the occupation, which is why I did this track run. However, I just assumed that it would be going along at some level, and then perhaps someone kicked it, and so there would be a small jog, and that would be its new position. I did not expect to see the site move and then move back, apparently. So I assume maybe what had happened is I spoke to the teacher when the children were gathering here and we were setting up the sites. They were very interested in seeing what we were doing. So I just explained to the teacher what we were doing here, and I kindly asked him to make sure that the children don't get too close, block the signal, potentially disturb the equipment. So what I suspect happened here is that in the evening, 8:30 local time, someone came along, didn't like the equipment for some reason, and just decided to lay it on its side or push it over for some reason that is not known to me. But then the next morning at 7:20 local time, perhaps the teacher or some other very kind local decided that, having seen the equipment on its side, they would put it back so that we would not have our experiment disturbed. And that was very good of them, but unfortunately they didn't put it back in exactly the same position, which we discovered later. But in this case, we have about 9 hours of very good data at the beginning of the session. We have several hours overnight, California time, of bad data that we definitely don't want to use. But then we have this data from after the antenna was put back in position, which technically is static data. It's good. It's just that the antenna was not directly over the mark and it had a slightly different height. But because we measured the new height and we measured the horizontal offset of the antenna in this area, we could actually still use this data with different numbers in the station.info file. Now you remember in the station.info file that we have a height, antenna height column, but we also have a column for north and east offset from the mark. Normally those two columns are just 0 because you measure directly above your mark, which is what happened in the first period. But in the second period, we measured an offset in the north and east. And if you do that, then you could actually include non-zero north and east columns in station.info file and use this data as well. So that's the end of this talk, just showing you a few of the examples there. Thank you for listening.